Hi everyone, in this video we are going to see how to find the equations of the direct common tangents and the common chord when two circles intersect. Let's suppose we have two intersecting circles like this. Their equations have been given here. For this type of relative position of two circles, we can have two direct common tangents and also we can have a common chord. Here I am going to do a little bit of construction. First I am going to connect the centers of the circles and then I will be drawing the direct common tangents and the common chord. Next, I am going to assign a name to each of the important points. Let's suppose the direct common tangents intersect at point D on the extended PQ line. And also let's assume that the yellow dotted line is the common chord. Let's assume that P is the center of the first circle where the coordinates are negative g sub 1, negative f sub 1 according to the given equation. And let's assume that the center of the second circle is the point Q whose coordinates are negative g sub 2, negative f sub 2. Let's assume that A and B are the 2 points of contact for the first direct common tangent which is on the upper side. Next, I am going to join P with A and Q with B. Now, what would be the radius of the first circle? Well, from the given equation, we can say if the radius of the first circle is r sub 1, then it will be square root of g sub 1 squared plus f sub 1 squared minus c sub 1. And similarly, the radius of the second circle, if we assume it to be r sub 2, that will be equal to square root of g sub 2 squared plus f sub 2 squared minus c sub 2. Now, if we look at the two triangles here, triangle APD and triangle BQD, you will notice that we have a pair of right angles there. The angle PAD and the angle QBD, they are actually 90-degree angles because we know radius is perpendicular to the tangent at the point of contact. Also, since AP and BQ, they are perpendicular on the AD line, so AP and BQ, they will be parallel to each other. Then the angle APD and the angle BQD, they will be equal angles because they will be corresponding angles between two parallel lines. And also the angle ADP, that is a common angle between the two triangles. So we can see that between those two triangles, their corresponding angles are actually equal. That means those two triangles will be similar triangles. And because they are similar triangles, we can say that the ratio of their corresponding sides will be equal. So I have noted it up there. And I'm going to take the first part of the proportion. And that can be written as PD over QD is equal to AP over BQ. Now what is AP and what is BQ? Well, AP is actually R sub 1 and BQ is actually R sub 2. So we can write PD over QD is equal to R sub 1 over R sub 2. And from here we can say PD is to QD is equal to R sub 1 is to R sub 2. That means we can see that D divides the PQ line segment externally in the ratio of R sub 1 is to R sub 2. Now, if we assume the coordinates of D to be x sub 1, y sub 1, we can use the section formula to easily calculate the value of x sub 1 and y sub 1. So, the value of x sub 1 will be like this. Here I have used the section formula for external division, and similarly the value of y sub 1 will be like this. So now with all the given information, we have been able to find the coordinates of the point D. So now let's try to find the equation of the direct common tangents. Let's assume that the equation of the direct common tangents is a generic equation like this: y minus y sub 1 is equal to m times x minus x sub 1. As you can see in the diagram, there are actually two direct common tangents whose slopes are obviously different. So here I have to find two different values of m. So somehow we have to come up with a quadratic equation in m, and from there I have to calculate the two possible values of m, and then we can plug in those values of m in this generic equation to finally derive the equation of the DCTs. And when I say DCT, please assume I mean direct common tangent. Now, if we change the equation a little bit, we can rewrite the equation like this: mx minus y minus mx sub 1 plus y sub 1 equals 0. That's the general form of the equation of the direct common tangents. And here we have to somehow find two values of m. And for that, we are going to use a different technique here. We know that the distance of the point P, which is the center of the first circle, so its distance from the direct common tangent would be equal to the radius of that circle. So we can say that the distance of the point P whose coordinates are negative g sub 1, negative f sub 1 from the DCT is equal to r sub 1. We know the DCT's equation, which is a general equation right here, and also we know this distance is equal to r sub 1. So if we use the formula for the distance of a line from a given point, we can say that the distance would be r sub 1 and the distance will be like how I have on the left hand side of this equation. So this is the equation that is going to help me find the two possible values of m. So from here, from this new equation, if we bring the denominator to the right hand side, we can write the equation like this: And next we have to get rid of the absolute value sign, so we can take a square on both sides, and then our equation would look like this, and the right hand side can be written like this. If we remove the parenthesis, then the right hand side would look like this, and on the left hand side I got rid of the absolute value sign, so our equation looks like this. And then if we expand the left hand side, our equation would look like this, and if we bring everything to the left hand side, our equation looks like this. And if we rearrange the terms a little bit, our equation can be written like this. And if you carefully notice, this is actually a quadratic equation in M. M is the only unknown here, because we already know the values of G sub 1, F sub 1, X sub 1, Y sub 1 and R sub 1. The only unknown here is M. So from this quadratic equation, we can calculate the value of M using the quadratic formula. And the two possible values of M can be written like this using the quadratic formula. I am using the plus or minus sign there. Now let's use the plus sign to calculate the first value of M, and let's use the minus sign to calculate the second value of M, and let's name them as M sub 1 and M sub 2. So then the equations of the DCTs would be like this: y minus y sub 1 is equal to m sub 1 times x minus x sub 1, and the second one will be y minus y sub 1 is equal to m sub 2 times x minus x sub 1, and those are the two equations of the two direct common tangents. Next, let's try to find out what is the equation of the common chord. The equation of the common chord is actually s sub 1 minus s sub 2 equals 0. I have already created a separate video on this topic. I have shared the link in the description. Feel free to watch that video. There I have derived the equation of the common chord to be s sub 1 minus s sub 2 equals 0. Now what is s sub 1 and s sub 2? Well, s sub 1 is the left hand side expression of the equation of the first circle, and s sub 2 is the left hand side expression of the equation of the second circle. With this notation, the equation of the common chord would be s sub 1 minus s sub 2 equals 0. And if we plug in the values of s sub 1 and s sub 2, the equation will ultimately look like this: 2 times g sub 1 minus g sub 2 times x plus 2 times f sub 1 minus f sub 2 times y plus c sub 1 minus c sub 2 equals 0. I hope things are clear up to this point. Next, we are going to take an example. Find the equations of the DCTs and the common chord for circles x squared plus y squared minus 4x minus 4y plus 4 equals 0 and x squared plus y squared minus 10x minus 8y plus 32 equals 0. So let's get started with the solution. If we compare the equation of the first circle with the general form of the equation of a circle, then we can say that g sub 1 will be equal to negative 2 and negative g sub 1 will be equal to positive 2. And similarly, f sub 1 will be equal to negative 2 and negative f sub 1 will be equal to positive 2. So the coordinates of the center of the first circle would be 2, 2, and let's assume that point to be P. And what would be the radius of the first circle? Well, let's assume it is r sub 1, and that will be equal to square root of g sub 1 squared plus f sub 1 squared minus c sub 1. And now let's plug in the values of g sub 1, f sub 1 and c sub 1, and the radius turns out to be 2 unit. Similarly, let's compare the second equation with the general equation of a circle, and from there we find g sub 2 is equal to negative 5 and negative g sub 2 is equal to positive 5. And similarly, f sub 2 is equal to negative 4 and negative f sub 2 is equal to positive 4. So the coordinates of the center of the second circle would be 5, 4, and let's assume that point to be Q. So Q's coordinates are 5, 4. And now what would be the radius of the second circle? Let's assume that to be r sub 2, which will be equal to square root of g sub 2 squared plus f sub 2 squared minus c sub 2. And now let's plug in the values, and that radius turns out to be 3 unit. Now let's calculate the distance between P and Q using the distance formula, and the PQ distance seems to be square root of 13, and 13 is actually greater than the difference of the two radii but less than the sum of the two radii. That means the two circles actually intersect each other. So in this case there will be two DCTs and a common chord. So now let's try to find the equations of the direct common tangents. Let's assume that the direct common tangents intersect at point D, whose coordinates are x sub 1, y sub 1. We know that D divides PQ externally in the ratio of r sub 1 is to r sub 2. So using the section formula, let's try to calculate the values of x sub 1 and y sub 1. X sub 1 turns out to be negative 4 and y sub 1 turns out to be negative 2. So the coordinates of D are negative 4, negative 2. Now let's assume that the equation of the direct common tangents is y minus y sub 1 is equal to m times x minus x sub 1. And if we plug in the values of y sub 1 and x sub 1 and transform the equation, it's going to look like this. Now using this equation, let's try to find the distance of the DCT from the center of the first circle, which is point P, and that distance obviously will be the radius of the first circle, which is equal to 2 unit. So if we use the formula for the distance of a straight line from a given point, we can write it like this. I am simply using the formula. I have already done a separate video on this topic. I have shared the link in the description. Feel free to watch that video. And from this new equation, we are going to calculate the two possible values of m. We want to convert it into a quadratic in m, and then we will find the two possible values. If we bring the denominator to the right hand side, then our equation would look like this. And then if we simplify a little bit, our equation would look like this. And if we take 2 as a common factor on the left hand side, then our equation would look like this. And then finally we are going to divide by 2 on both sides. Then our equation would look like this. Next, I am going to take a square on both sides to get rid of the absolute value sign and the square root. If we take a square, it will look like this. And then getting rid of the absolute value sign and the square root, our equation looks like this. And if we expand the left hand side, our equation looks like this. Next, let's bring everything to the left hand side, then our equation would look like this. And upon further simplification, our equation looks like this. And from here, the two possible values of m would be like this. I am simply using the quadratic formula. And if we simplify that, the values of m would look like this. And if we simplify a little more, the values of m would look like this. And finally, the values of m would look like this. 3 plus or minus square root of 3 over 4. Let's take the plus sign for the first value of m and let's call it m sub 1. So m sub 1 can be written like this. And if we take the minus sign for the second value of m, then we can say m sub 2 is equal to 3 minus square root of 3 over 4. So we have found the two possible values of m. Now let's plug in that value in the equation of the DCTs. The general equation of the DCT was like what you see at the top here on the top of the screen in the light green box. So there I am simply plugging in the values of m. So first I am plugging in the value of m sub 1 to find the first equation. And if we simplify that a little bit, it looks like this. And if we simplify a little more, then our equation finally looks like this. So this is the equation of the first DCT. Now let's try to find out the equation of the second DCT. We are going to use the value of m sub 2. The equation of the second DCT would look like this. Here I have simply used the value of m sub 2 in that same generic equation, and finally our equation looks like this. So we have found the equations of the two direct common tangents. Next, let's try to find the equation of the common chord. Well, we know the equation of the common chord is like this. S sub 1 minus S sub 2 is equal to 0. In this case, S sub 1 is actually the left hand side expression of the first equation of the circle, which is x squared plus y squared minus 4x minus 4y plus 4. And S sub 2 is the left hand side expression of the equation of the second circle, which is actually x squared plus y squared minus 10x minus 8y plus 32. So if we subtract these values, then the equation of the common chord would look like this. And if we remove the parenthesis, then our equation looks like this. And there you see the positive x squared and the negative x squared, they will cancel out each other. Similarly, positive y squared and negative y squared will also cancel out each other. And we are going to be left with 6x plus 4y minus 28 is equal to 0. And if we divide both sides by 2, then our equation becomes 3x plus 2y minus 14 equals 0. And that is the equation of the common chord for these two circles. I hope everything made sense. Thank you for watching. See you in the next video.